about reliable and scalable robot communication.
You lucky people, you get a double dose. Okay, so this is again someone else's work, primarily Andrea Ruta, but also Natalia, and our colleague Gerardo is somebody who does robotics in some kind of serious way. So, common outline, background, what did we build, how, what did we learn. So we're doing robotics, and one of the big efforts in the robotics community is around something called ROS, the Robot Operating System. It's open source, so similar to the Erlang ethos. It's a fairly standard collection of tools, libraries and conventions. It's widely used in the academic community and in small industrial deployments. It's not used in many large industrial deployments, and I'll explain why, but the motivation is no one lab can build entire robotic systems. It makes sense to have a common set of drivers and libraries and reuse them. And it's quite widely used over the world, in North America, Europe, Japan, and then smaller numbers of users elsewhere. It's fairly flexible. There's a whole bunch of stuff. It's Unix-based, process-based. You use a bunch of libraries, and you use as much or as little as you need for your application. And people are encouraged to make pull requests to improve the libraries. So the idea is you have a bunch of nodes. ROS nodes are essentially Unix processes. They have a communication structure which is basically publish, subscribe. There's a single ROS master that controls everything. And the hope is that people produce useful libraries and make them ROS compliant and make them available to the community. Having a single master node has huge problems for reliability. It's a single point of failure. All of the ROS nodes are registered with the master. It doesn't have sensible monitoring and recovery mechanisms, although you'll see that it does have some, and in fact we use them, and I'll show you the results. There's a second version called ROS2 under development, and it will address some of these issues, including replacing the single master with replicated masters, but it's like a band-aid. It's not going to fix a lot of the big problems. The match between Erlang and robotics has been observed before. Lightweight concurrency. In some sense, a modern robot is a distributed system. A modern sophisticated robot will have 60, 70, maybe 100 different devices that are all cooperating to do something, and robots often operate in teams, in which case you have even more. So that it's just essentially modern robotic software is a distributed system. Erlang's got the right kind of capabilities there. Soft real-time, lightweight scalable concurrency, and reliability. So various people have used Erlang in the robotic context, building frameworks and simulations, attempting to build an entire robot operating system in Erlang from the ground up, which was very brave. And then the curl project between Kent and RWTH Aachen pretty much teaches Erlang using robots. If anyone remembers Turtle Pascal, it's kind of the same thing. Robots are really engaging, and when you see them do things, it motivates programmers to write code. I guess our idea is slightly different to either of those projects. We're not really trying to build an entire robotic platform. We're trying to keep ROS as far as possible. And we're not trying to teach Erlang. Rather, what we're trying to do is take out the communication layer between the ROS nodes and replace it with a reliable Erlang communication layer, because we think that will help the reliability properties of robotic software. And this is really a feasibility study into that approach. To do it thoroughly would require a lot more work. So what we did was to build and measure a typical robotic application using ROS, or using only ROS and only ROS and its publish subscribe communication, or to use ROS with Erlang communication and reliable Erlang communication to supervise Erlang processes. The application is a face tracker, so you have a video feed from a camera, but the camera is sitting on a pan tilt head, and the video stream is analysed to detect someone's face, and it tracks the person's face as they move. And then you feed the tracking information back to the camera actuators, and you move the camera to track the face. So it uses a whole bunch of existing software, face detection. These things are called classifiers, and you use a whole bunch of them. Standard camera control software, and user interface stuff so that we can produce pictures like this. So that's Andrea, and the face tracker has identified this section of the image. Okay. What are the software architectures? So we're building two systems for various metrics. So in the ROS world, we have the camera. It streams video to a bunch of ROS nodes. We have a whole slew of workers. What these are doing is they're running different face classifiers. So there's a whole bunch of face classifiers. You aggregate the information from these classifiers back to come up with your best guess using a bunch of different classifiers, and based on that best guess you drive the camera to now point at where you think the person is. Erlang world, well, there's still quite a lot of Python stuff here. So the camera control is a Python piece of Python code. The classifiers are also chunks of Python, but there's kind of an Erlang coordination layer here that is taking the images, passing them to the classifier, picking up the classification information, forwarding it to an aggregator, and then, well, actually it's aggregation processes connected to the camera control. There's three supervisors in the Erlang software. Top level supervisor, one for all of the face detectors, so all of these worker nodes, and one for the aggregator. How does the code compare? Well, there's a few more modules in the Erlang world than in the ROS world, and there's about 50% more code. In particular, one thing that's really noticeable is that the ROS communication, because you just call a magic publish library call, it's a single line, whereas you actually have to write some message passing in the Erlang world. So you have to write a bit more code, but it's not a huge amount. So we did a bunch of experiments using a fairly bog standard laptop. The details of which version of ROS, etc. are listed in the paper. So the first thing is, how many face classifiers can you run? And to be honest, you probably don't want to run as many as 700 face classifiers. But we were interested in using this piece of software as a basis for experiment. So in the ROS world, you can run about 200. In the Erlang world, so this plots the number of workers, the number of processes, against the time, the processing time. In the Erlang world, you can run 700 or so. But you'll notice that the time to run grows, and I'll say more about that shortly. So, I guess the key number on the slide is you can run 3.5 times as many Erlang processes as ROS processes. What about memory? Well, there's a main node which is slightly bigger than everything else. In particular, the Erlang VM is quite big. The Python workers are bigger in the ROS world than they are than the interpreters that are called from the Erlang world. Consequence is we use about half of the memory. This latency, the times we were reporting, what activities are contributing to that execution time? Well, the time to ship data from the main node to the worker nodes, so this is going back through this architecture, to get it from the main nodes out to the workers is very little. The time that the workers take is considerable, the time to get it back is quite short.
So, what is this 50 instances in the previous slide?
Oh, I think this is this configuration had 50 face classifiers.
Okay.
So
So it's not like the 200. We saw something before with variable.
200, yes. Yes, that's right. This is with 50 face classifiers. We could have repeated this experiment with 200 maybe. Yeah? Yes. I guess there's probably an abstract equation you could give. It's parametric in the number of classifiers you're running. Yeah.
And what are Python interpreters in the Erlang version? Are those Unix processes, or are those Unix processes?
They are, yes.
Okay.
Okay, so this is in the ROS world. Shipping the data around is fast. Actually doing the detection is what's taking all the time. Well, the detection time in the Erlang world is very, very similar to the detection time in the ROS world. That's deeply unsurprising. They're using the same open source classifiers. The time to ship the data around, to get the data from the camera to the Erlang process is small, as is the time to get it from the Python detector to the aggregator. But getting it from the Erlang processor to the Python detector grows with the number of processors. And this is why the Erlang processing time is growing. And this is all down to the library that we used to ship the data from the Erlang world into the Python world. So the learning there is use an appropriate library if you're hoping that your software will scale.
Do you think it can be mitigated? Do you think it can be mitigated with a better library?
Yeah, definitely. It should be. Foreign function interfaces shouldn't take huge amounts of computation, and they should behave in a scalable way. We just saw something nifty that I think should do that. Even though talk. Okay, what about the quality? Are we getting the same results? Well, the key metric here in video analysis is something called the Jacquard index. Here we have the real index is a green square. The computed estimated face is the dark blue square, and the overlap between the two is in this light blue or cyan. And what you're trying to do is to get this overlap to be as big as possible while minimizing the bits of the image that you haven't captured, and also any kind of false positives, things that you think are the image. And this formula, which is essentially you want to get the overlap to be as big as possible so that this tends towards 1. If you have a perfect overlap, if your face detector is perfect, you'll get a value of 1. And if it's completely rubbish, you'll get a value of 0. Well, if we compare Ross and Erlang face detectors, they have very similar performance. We have measured them with different numbers of images being aggregated. I thought initially if you aggregated a whole bunch of images you would get a more accurate prediction, but the problem is that the face has moved and now you're getting where the face was 10 images ago, and it's confusing the detector. So in fact you get the most accurate detection by classifying just a single image for both systems. And the quality of the two systems is very, very close. So essentially the Erlang version is producing almost the same quality as the Ross system. What about reliability? Well, we measured this again by using Chaos Monkey-like scripts, one in the Python world, one in the Ross world, and one in the Erlang world, to kill classifier and aggregator processes, about 200 processes a second. In the Ross world, well, and we used either a fairly gentle kill or a brutal kill. The recovery times are about 1,000 times faster in the Erlang world. These are Unix processes, so they take quite a while to recover. But they do recover, so Ross actually does provide reliability at this level. But it's slow because you're recovering Unix processes. Does this difference in time make any difference? Well, let's look at the quality of the face tracking of the images when you start killing things. So here we have time advancing to the right measured by the number of frames, and at some point, it's around about frame 21 here, frame 26 there, we start killing the Ross processes or Erlang processes. What happens to the frame quality? Well, so the green line is the good quality that you'd like to maintain, the absolute quality. The red line is what happens if you use sig kill, and blue line is with sig term. And you see the quality drops quite dramatically for Ross. It drops for Erlang, but not as low, and it recovers more quickly. So, you're running a face tracker, it's trying to track someone's face. How good is the face, what's the quality of the face classification that you're getting? Well, you lose quality when you start having failures, because the system is committing its compute time to recovering failed processes. But the Erlang world recovers faster, and I think the drop in quality is less. I see some confused faces. Does anyone understand what I'm saying?
So what happens to the green and the blue lines there? What is this x-axis?
It fully recovers. It matches the red line.
Yeah. Yes. Once the red line is back over the green line is invisible. So
on the left there with the red line when it bottoms out here, on the left.
On the left.
Left.
The other left.
and here, good question. I don't know. Something obviously happened, and I don't know what it was. the message is the Erlang processes recover faster and it has less negative impact. And there's a whole slew of these graphs in the paper. We looked at what happens when you fail 50% of the workers, when you fail 25%, 10%, and 90%. And the pattern is subtly different, but people are already struggling to understand a single graph. There's more experiments in the paper. What do we conclude? Well, this is, as I say, it's really a feasibility study where we've looked at scalability and reliability, properties, time scaling and memory scaling of fairly typical robotic application, face trackers. Again, they're a small kernel. It's not a serious robotic application, but it does have data input, analysis and control. It's, somehow a representative kernel. The Erlang communication scales better. You can support 3.5 times as many processors with only half of the memory. If you want to keep the processing time under control, you better use good foreign language libraries, otherwise you're going to run into problems. The restart of lightweight Erlang processes is so much faster, deeply unsurprising compared with restarting Unix processes, but crucially these have different impacts on the quality of how the device, how the robotic system works. What's next? Well, we could use different kinds of face trackers. We could do more on the memory consumption, as Kostis said. We measured at one point, you could look at an analysis with scale. But we think this has been quite a positive feasibility study, and we've actually purchased a bunch of robots. There's little mobile car things that have a camera and a little Raspberry Pi sitting on them, and we think that we could more systematically replace the communication layer in ROS with a reliable Erlang-based communication layer that would scale better. So currently in the ROS world, if a single ROS node fails, it poisons the entire system, and well, it often poisons the entire system, and people who work with robots have to manually restart the robots. So we think that Erlang technologies, if we produced a new communications library for ROS, it could really improve robotic software. And that's something we'd like to do.
So the question about, can you go to the architecture slide, please?
Architecture slide.
Yes. So the architecture in terms of resiliency, when you, in the Erlang mode, when you kill the Erlang worker, or what exactly is killed? Is it only the Erlang process? And what does happen with the Python interpreter, which is associated with this given Erlang detection worker?
Good question. So there's, given those restart times, I guess the newly created, so when the worker is killed, the supervisor detects that and restarts it. I think it must reconnect to the Python, the existing Python interpreter. I didn't write the code, but given those recovery times, it there isn't time in that recovery time to restart a Python interpreter.
How invasive is this from the point of view of someone writing these components? Do they have to modify their components?
Yeah, so feasibility study, we hand wrote this Erlang. These Python classifiers, so we hand wrote this stuff. When I talked about building a new communication layer for ROS, that would be to pre-package this kind of structure and provide it in a library that can just be called from, well, probably ROS2, either ROS or ROS2. So this was a hand-built framework for the purposes of experimentation. But your point is absolutely right. If you want anyone to use this, you can't tell ROS people to go away and learn Erlang. What you have to do is you have to provide a magic library that makes their world much, much better and uses Erlang under the hood. So that's that plan for
Okay, so you think it's really feasible to provide it as completely as a more or less transparent backend?
we'd say a communication middleware, yes, but it's under, it'll be under Unix, it'll be Beam VMs running as Unix processes spawned from a library. ROS is in the open source Unix world. Well, our vision is that we can make it seamless. We'll find out when we built it if anyone uses it. Patrick.
So, if you have mobile robots, then maybe communication indicators will be much more common than actual node robots. And I don't really know. Does Erlang have special abstractions to deal with these? The process restart doesn't seem to be the right response for that.
Well, that's one of the things we're really interested. That's kind of one of the reasons for going into mobile robots is so that one of the things we'd like to deal with is lost and regained connections between ROS nodes. And currently, ROS doesn't handle that at all. So we'd have to build mechanisms for dealing with both losing connection to some ROS nodes and regaining it. Yeah.
Do the OTP libraries currently have some kind of behaviors that do these things already?
I point to the people in the room and ask them.
Some question about the memory consumption. So, if you go to the slide, if I remember it correctly, that one. So, it looks to me that most of the memory is spent in Python interpreters.
Yep. Yes?
And there are two questions here. First is, why do you have such a difference between the worker nodes and the Python interpreters? And it looks a slightly big difference here. The second is, no matter what we do in the Erlang, if you don't improve the Python interpreters, then...
Right. I'm not sure. Well, I believe the answer to your first question is these Python workers are being wrapped up as ROS nodes, so publishing and subscribing. Subscribing to a stream of video frames and publishing their results. So I think that's probably where the extra memory comes in, but I'm not certain. I think the answer is probably in that section of the paper. And yeah, you're right. So, and it's kind of unsurprising given this this architecture. Essentially, Erlang here is being used as a coordination framework. So and it's providing, if you like, a reliability, well, a work distribution and reliability wrapper around a mostly Python system. And hence, most of the code and most of the memory is being consumed by the Python computations that are being coordinated. But we think that would probably be really typical of how, if we build the ROSI library, a communications library, that would be absolutely typical. The Erlang stuff would only be a kind of coordination and resilience layer, and most of the heavy lifting would be kind of C drivers and Python stuff. John?
So, again, coming back to this architecture, in the results you showed us for resilience, then you're saying that the very quick recovery time of the Erlang system is because it's the Erlang process that is being killed there. But the Erlang process is something very small and simple. Most of the hard work is being done in the Python node, right? So, in reality, if there's going to be a crash, why should it be the Erlang that crashes? It's surely much more likely to be the Python node that's doing the hard work that crashes, in which case you don't get benefit. So maybe the lesson is, if you want your face recognition to recover fast, you better not write it in Python. There isn't time to restart the Python node and get quick recovery.
Yeah, I can't agree. Yes, but
Yeah, so does OpenCV has binding, are there bindings for Erlang to OpenCV?
I don't know. I didn't write the code. The answer might be in the paper. Yes?
The scalability limit is 700 versus 200. Is that basically explained by running out of memory on your machine? Because you have higher memory requirements for the also.
I don't know which resource limits the scalability.
Well, you know how much memory you should have.
16 gig.
Fits.
15,
So
4 gigs, yeah.
if we, you mean doing the arithmetic here? Yeah.
Other questions? Thank you.